Okay,
Sure.
yeah, however you want to start.
All right. Um, okay, so I think you guys can see the paper. Okay, cool. So yeah, thank you so much for coming on for this paper discussion. I really wanted to uh, understand what these authors have come up with, and so there you go. That's why I was like, yeah, fair enough. I'll just host this. So this paper, what it tests is like, given we have a lot of computer vision models, like based on transformers, convolutional nets, and the author just wanted to see how well these computer vision models, which there are a lot of them now, compare in predicting the brain activity using the NSG data sets. So they used around 224 different models, and they tested different aspects of it. Basically, um, they describe an inductive bias, which means that just having one thing different from each other and keeping all the things same. So I'm just gonna dive in deep into what the things they actually tested on. So testing out 160 pre-trained models and 60 untrained models. So they tested 224 models on the NSD data set, and that came across around 1.8 billion regressions just in testing. And that's what this 1.8 billion regressions, in the title actually means. So in the testing, they actually did around 1.8 billion regressions. That's kind of crazy. But yeah, so they tested out how. So first of all, it does not predict fMRI like the fMRI voxels. I wish it did. But what these authors did was, get a pre-trained model or an untrained model, pass an image through it onto a higher dimension lattice, right, and pass the fMRI in a similar encoder to get it onto the same dimensions, get the vectors of the same dimensions, and then compare those two embeddings and get a Pearson score, which defines how well two embeddings are correlated with each other. So by changing different parts, either it might be a model or different, different models which are pre-trained on different tasks, and a whole lot of things. It actually the authors came up with what kind of parameters should we change in order to achieve the highest brain activity. So wait, give me a sec. Okay, so that's what the paper is all about. So first of all, uh, here we see. Yeah. So before that, getting into detail about what were the things that were actually, what the authors actually discussed, they used two types of linking methods, which were used to compare the two embeddings. So here they've used classic RSA, or representational similarity, uh, what is it, analysis, and VERSM. I mean, if we go more into detail about it, these two are also the factors in determining how well the model embeddings correspond to the brain activity. So so the classic RSA is just, it assumes that each layer of the model contributes equally to predicting the voxel level brain predictivity, which basically means that each part of the model is contributing equally. Whereas voxel level and voxel encoding RSA, it assumes that some parts of the image lead to different parts of brain which are being activated. So it's not equally divided, in the sense that given an image, uh, it's not necessary that each part of an image will equally activate that part of uh, you know uh, that part of OTC, which is like human occipitotemporal cortex. So voxel encoding RSA assumes that it is reweighted. So the weights of the encoders are reweighted, and not every part of the image corresponds equally. So if you want to deep dive into like how exactly they calculated, it's mentioned right here. But in a gist, what exactly so I've just explained what's the gist of these classical RSA and voxel encoding RSAs. And it really, and this is also actually a factor in determining how close are we to predict the brain predictability. So, yeah, okay.
I
Mm,
actually would like
yeah.
to understand better the specifics of what are they actually doing with this RSA. So they have all these models. For every
Mhm.
given model, they do say classical RSA between the occipitotemporal cortex voxels, um, correlated to, for every layer of the model, the projections
Yeah,
from that layer, and then they pick the best fitting layer as
exactly.
what they pick. And for
Y-
the VERSA, it's the same thing except they allow the,
Reweighting.
the reweighting.
Yeah.
So how do you get from like a model layer of an arbitrary number of features to the same dimensionality as the voxels to do the
Like as in,
correlation? Because the RSA
uh,
is like a correlation matrix, right? So
yeah,
you're
yeah.
correlating the voxels to the features of a
Mhm.
given layer of the model. But the number of features in a model might not, or it's usually not going to equal the number of voxels. So how do you
Yeah.
do the dimensionality changing to do correlation for it?
They actually, even before they get into that, they actually reduce the dimensionality. So, this is where they mention, yeah. So they reduce the dimensionality using the sparse random projection. See, now this is the part of machine learning that I'm not very familiar with. So I'm not really good with the details. So they did reduce the dimensionality mostly because if we are looking at models such as like BGG, in their deepest of the deepest layer, it could have like 3.2 million dimensions per image. And that's like too many for them to handle. So they reduce it down to a target dimensions. And after that, they start, computing the sparse random projections for each layers of the deep learning model. So, so reducing the dimensionality plays, it's like the first thing they do. I think that's what they use to equalize the dimensions between the brain voxels and the image
So
uh,
like as
latents.
an
Yeah.
example, then let's say that a model layer has 100,000 features and occipitotemporal cortex has, I don't know, 5,000 voxels. I don't know how many voxels are in
Mhm.
it, but you have to basically make it, so you take the 100,000 features, you have to make it 5,000. Random projection without reweighting means that you're basically selecting 5,000 of those 100,000 and not altering them at all.
Oh, for classical RSA, yeah, I think so. Although this is something I need to read more about, because although it does play a part in explaining what other features do to a network, we should really understand this. So yeah, this is something I should really
Like
read into
they have
because
to pick,
yeah,
right? They have to somehow determine how they're gonna pick those 5,000.
yeah, uh, yeah. It's actually interesting how they actually do it. I need to. I actually did not read in detail about how they actually calculate it, although they do use so most of the models, if we look at it once we go ahead, it's like the classical RSA score, the Pearson coefficient of classical RSA is generally at a lower rate, than compared to the voxel encoding RSA. So it just suggests that reweighting those, uh, the applying the reweighting over those layers is actually, yeah. So there's this metric that reweighting actually explains 79% of the variance of the of the voxels of the NSD data set, while the classical RSA just explains like around 31%, which means that uh, like there is a lot of variation across in the classical RSA that we just cannot explain. So it's like reweighting really helps us explain, helps us realign those image vectors with the brain voxels. And yeah, so I should really just get into how they actually do it. I actually wasn't even familiar with RSA before this, so really need to
Yeah,
do some reading about it. Yeah.
yeah. I just one more question then. They do the random sparse projection both for classical and for the voxel-wise
Um,
RSAs? They reweight the outputs of the random projection, or they reweight before the, or they like,
no, they reweighted after.
so they do random projection for both, and it's the only difference is they also reweight afterwards for voxel
Mm,
encoding.
the computer. See the see the thing is, I'm not familiar with what's representational similarity matrices. Uh,
A
so
represent
I
it's
co
just a complicated way of saying a pairwise correlation matrix, I believe. Like, um,
oh, is it that? Um, not too familiar with it. Although I will definitely get back into this. This is something that I think I need to delve deeper down into the math of it. Yeah. Sorry, this is not the outcome I actually expected. I will actually get deeper into it. But
yeah, I
yeah,
mean it's
it's
getting
like
into the weeds a bit, but yeah.
Hmm. It's like these two metrics are constantly being used to measure how good of a brain mappings we have. But even in the paper they mentioned, we don't the authors don't actually know which one actually is better than the other. Although we see the classical RSA's Pearson score is not actually that good across all of the factors across all of the models as compared to voxel encoding, but it does not actually mean that like the voxel encoding RSA is statistically more significant than classical RSA. So, although if you just think about it, it can't be true that each part of an image constitutes equally to the activations in your brain. It has to be like some parts of the brain will contribute more. Anyway, just some thinking top of my head. So, uh, as far as the mathematics goes into it, I'll have to look deeper because even I wasn't familiar with RSA and what the
So the
representation matrix is. Yeah.
the RSA is pretty simple. It's pretty much just what Paul said, where you extract the features for, in this case, 1,000 images. You construct the matrix 1,000 by the feature dimension. Say feature dimension is like 5,000. You got 1,000 by 5,000. Then you just compute the correlation matrix within, like separately for the model and for the brain data. And so you get 1,000 by 1,000 correlation matrix for each case. And then you just correlate those two correlation matrices. And it basically
Mhm.
just measures whether like the geometry of the features is similar in the two model and brain. And in this way, you don't have to worry about the difference in feature dimension because you only correlate within the two, like you correlate within the model and then within the brain, the features separately, and then just
Mhm.
compare the correlation matrices, which are the same shape.
Right. Also, essentially just correlates. Okay. Hmm. Yeah, that makes sense.
One
Um,
other one other
yeah.
to bring up at this point is like you talked earlier about a little bit about how you wish they were doing, how you wish they were predicting brain activity instead of doing this RSA. I kind of looked at the
Mhm.
voxel encoding RSA as effectively just another way to measure brain
Mhm.
activity prediction performance because the weights are given by just a like a trained linear encoding model.
I just said that in the hopes that it would be helpful for us for the Algorithm challenge, and that's all. Yeah, so
Oh,
it
right,
is
right, right.
a
Got it.
direct correlation of the fMRI activation. So
Right.
it
Yeah,
will be helpful for us for Argonauts, that's all.
got it.
Yeah, yeah. So um so where were we? Okay. So yeah. So to test out if these brain activations are actually correlated with the uh, the high level latents of the image. What the first authors wanted to do was to test out whether there's a difference between using a CNN based models versus the transformer based, because because the CNNs have like this convolutional bias, so using convolutions, the mathematical concepts of convolutions to extract the features of the image, which is actually similar to how we humans correlate we perceive visuals. So, so whether to test out if this convolutional bias will actually affect the brain activity, the predictive brain activity. And well, the results was like not so much in a sense. Both transformers and wait, give me a sec. Yeah, so both transformers and CNN based architecture were equally were predicting equally well the OTC structures. So both had like a Pearson score of around 0.67 and 0.66 for transformer. So just a 0.01 increase. So there is no actually, so statistically speaking, both models were good at predicting these brain activations, but uh, VITs but when comparing the accuracies of these two, VITs were less predictive than CNNs on average when compared to when comparing the both CRSA and VERSA metrics. So the reason might be because of this inductive bias that the convolution, uh, the mathematical operation of convolution is similar to how CNNs extract the features of the image and perceive those image. So that might be it. But both the models, with such a huge difference in the architecture, transformers using this multi-head attention, and first we break down the images and then we pass it on, as compared to convolutions where we use the filters and the kernels to extract features. Even if they have this whole different architectures, they are essentially predicting similar responses in the high-level cortex. So the models are actually converging at the same representation format, which means that the high-level latents are actually pretty similar, even though the models are very, very different. Here, as you can see, so these are the scores that I mentioned: 0.66 Pearson for the transformer and 0.67 for convolutional models. So it actually does not really depend. It actually does not differ if we use a convolution-based network as compared to a transformer-based network. So as compared, if we look into other architecture, it does not really vary. So the next these authors examined was the task variation. So the currently
Could
these
we,
yeah, go ahead.
sorry, I was just hoping
Go
to like
ahead.
a pause on this result for a little bit, because I think it's kind of
Yeah, go ahead.
interesting.
Yeah.
One thing that I saw got brought up in connection to this result, I wonder if we could talk about, is like something to do with the fact that all of these networks that are being evaluated here have been kind of like selected for good performance on ImageNet. Like
Oh yeah.
these aren't like 20 random models. These are like 20 of the best models that have been produced over the past decade plus out of thousands and
Yeah.
thousands of models that have failed.
Mhm.
And so I wonder what your thoughts are on how that should affect our interpretation of these results, that these are models
Mhm.
taken from, these are like good
Right.
pre-trained models taken from the internet, not random models.
Okay, so that was actually intentional on their part because they wanted to make sure that each of the models that were tested, they were tested on ImageNet 1K. So all of the models had the same data set with similar accuracies. So coming up, there is actually a section where they test out different models which don't have, which actually some of which actually do have the top scores for ImageNet, and some of them actually don't. So once we get into that, um, the authors find that there is actually no correlation at all between the top performance or the models which are not as good of a performers. Here, just to make sure that just to ensure that the only reason of uh, observing change is the fact that we're using a CNN. Is the convolutional bias is the reason why they've used these models which have been trained on ImageNet data sets, so like just one data set and have similar accuracies. So there is actually a section where they test models which don't have similar accuracies, and well, it does not really affect it. So yeah, that's how.
Cool.
Mhm.
One other quick question is, did you like notice any patterns in the ordering of the models? I tried to look a little bit. I didn't really notice any patterns in terms of like.
Uh, I
Yeah,
don't I don't think
this
so.
ordered
More
just
recent
because of
models.
the y-axis? Like they just sorted it by
Yeah,
y-axis?
yeah, they're like sorted by brain prediction score. I was trying
So
to
the
see like if
voxel
there's.
encoding RSA.
I mean, yeah, if you look at this QuizNet 1.0, it has like a score of around 0.63. Yeah, so I guess they're just sorted on the basis of their Pearson coefficient, but then again, it's not even a delta of 0.1. And that's actually one of the results of the paper. It's like comparing these models across convolution neural networks to transformers, most of their Pearson correlation score is less, the delta is like 0.1. It's not even that much. Uh,
Yeah,
yeah, so it's just,
I
I
don't,
guess they're ordered on
0.1
the basis
isn't
of.
like nothing though. Like point 0.1 is a noticeable
It's not
difference.
in the sense okay, so if we change a lot of these metrics, right? If we change whether we use CNN versus transformers, whether we use like the models with the top accuracies, like if we change a lot of these, a lot of these things in the models which affect the accuracy of the image on the ImageNet, but in terms of predicting the brain activations, the delta of 0.1 is all they differ at, and that's it. Like a lot of this paper actually, like the conclusion of this paper is like even if we have some features that can actually improve features of any deep learning model which can actually increase the accuracy of, let's say, detecting, in the object classification, it does not really translate into predicting the brain activations. So, yeah, this paper is kind of like is like saying ki even if you have a lot of things to improve a model, it might not necessarily improve the brain activations. That's one of the things.
do you remember what are the error bars?
What?
You see how there's little error bars on each of the individual plots? I mean, each of the individual markers. It's like each one is a little rectangle with the height.
Yeah, it
Error
should say in the
bars, error
caption,
bars
right?
over something.
I mean, the
Yeah.
captions for
In general, I think like, yeah, the differences are small, but the error bars are also pretty small. some of the differences look reliable. Like say like the best transformer versus the middle transformers. Excite versus whatever these other ones are.
Like around how much? 0.67.
It's tough to interpret whether these differences are reliable for sure, since they're kind of numerically small.
Yeah, like, and I mean, I'm curious about the order still, because let's say that they sorted it based on, yeah, the performance of the Pearson, right? But yeah, looking at the labels, it kind of goes in the order that you would expect of like SqueezeNet, ResNet 18 at the very bottom, and then NF ResNet 50 at the top. Like, it
Yeah,
kind of
totally.
follows, right? And I think,
Yeah, they're kind of the order they were released.
yeah,
I
and that
mean,
means
not
like the performance of the model going up can correlate with the Pearson going up.
Yeah,
it's a
I agree.
Connext L was released off like before, like after resonance. Is it that
It's
old?
true. Convenex is one exception that I noticed also.
Yeah.
They're both in the middle, so the difference is not huge, but it was interesting to me that Convenex is in the middle. And that Convenex is also a pretty different architecture within
Yeah.
the CNN family. It's pretty different. And
And it's a pretty new model, so like I don't think they'll just place it right over here. Yeah, I just think it's just on the basis of their Pearson. So that's
yeah,
because
that's
I think
definitely how
that's
it's sorted. But then,
yeah, it's just similar for transformers as well.
like looking at the models based on that sorting, trying to read tea leaves in terms of which models predict better. In the transformers, for example, you see mostly like vanilla transformers at the bottom and some more specialized like hierarchical transformers like the swing at the top.
Yeah. Mm. Yeah.
It's interesting, but I think the tea leaves are hard.
Mm. Yeah. Yeah. I think this is these results are just for just explaining the convolutional bias, if the presence or absence of them actually affects the prediction of brain activation. So yeah, so should I move on, or do you have any more questions or thoughts about this?
Yeah, I think we did this one pretty well. Go ahead.
Okay. So yeah, so this was just about whether or not having a convolutional bias. But the next one was whether what if we use the models which have different tasks? So not all of them have, the object classification. So they use different computer vision models, and some of them were actually self-supervised algorithms as well. And they also tested out whether the representation of images and aligning it with their captions actually help in brain predictivity or not. So let's just move down to the results. So they used so let's first talk about the taxonomy models. So basically using models which have different different they wanted to see if the models with different tasks can actually affect the brain predictivity. So they used from autoencoder to detecting depth, so depth perception to semantic segmentation and object classification, and this actually gave a pretty strong indication that the tasks actually matter. Even the surprising thing was the autoencoding. I mean, not really surprising, but the autoencoding yielded the least score, like of Pearson score of 0.077 and VRS score of 0.103. So one of the lowest scores. Uh, and the object classification relatively had the highest score of 0.436. which is not which is not as equal to the one previously that I mentioned. And these authors just mentioned that the object classification in the data set was not as varied as compared to ImageNet 1K. So that was their reasoning for, because at this point, my thought was, if object classification has the highest score, why is it not equal to the ImageNet? Because it also classifies images, but in this object classification, they used uh, I think the classification, the number of classes was like around 100, whereas in ImageNet it was like ImageK1K was like 1,000. So since it was like a 10 times, I guess the classes were like 10 times larger, it led to a higher correlation score when comparing these models with different tasks. So uh, that I think was kind of given, but yeah, that's kind of interesting. So yeah, that
So
was for
like
taxonomy.
for object classification doing the best for the taxonomy, like they're using all the
Yes.
same input diet, right? But the
Yeah, they're
tasks are
using the same.
different. So tasks do like the task of the model does make a noticeable difference. Is like the
Yeah,
takeaway.
yeah. So like you can't really use some model which does like, let's say, semantic segmentation and expect it to predict those brain predictivity. So even it mentions here clearly that in spite of taxonomy's larger training set of around 4.5 images, nearly thrice that of ImageNet 1K, it still has a lower uh, Pearson score. That's just because the classes are less and the data set is not that diverse.
Yeah.
So
Well,
this
I
was one
think
of the things.
that
Yeah.
that's kind of interesting because, just going off of the author's interpretation on Twitter, and I think most people's takeaway from the paper itself is that image diet is the by far most
Oh yeah,
important thing. But like
exactly.
that doesn't mean that the task doesn't matter. Like it still matters to some
Mhm.
degree.
Yeah. Oh no, if image diet is like the most important, like the task matters, I guess that's on the second, because clearly there is a lot of variation between image classification and just say autoencoder. So uh, yeah, I guess we can also think of it in a sense that um, an object classifier will have a better understanding of an image as compared to, let's just say depth prediction, like a depth perception model. So, or a semantic segmentation model. So an object classification model will have a better understanding of an image. So that obviously relates in terms of predicting the brain activations.
Yeah,
So
but
yeah,
also maybe it's only pronounced here because it's using such an impoverished image diet. Like maybe if it was using ImageNet or a better input diet, then the role of task doesn't matter much at all.
yeah, but all of these data sets are using the same data set. Uh, so the data sets are same. Even in the architecture, they use ResNet 50 as an architecture, each of the models.
No, I
So
but the input diet for the object classification is the indoor scenes, right? But if it
mm,
was instead
yeah,
ImageNet, then maybe the difference between the model
then it becomes the same model as the one that was, yeah. So
yeah,
if we use the ImageNet, then it'll predict more classes, which means it's using a different data set, having a diverse data set. But in this sense, that each and every model that was trained on is on the same data set, so we can so it really comes down to the tasks that were, the task of the model instead of the data set, since each of them are just using the same data set. This YFCCIM data set. So
Yeah,
Yeah.
I'm talking about like the takeaway. Should the takeaway be that input diet matters the most, followed by task based
Yeah.
on the orange plot here? Or should it be like if you have an impoverished image diet, then task matters a noticeable amount as number two. But if you have a very nice image diet, then maybe the task doesn't matter that much.
Yeah, so actually data set matters a lot because matters the most, I would say, because if we go down into the study, it's like they test out between ImageNet 1K versus 21K. So, and when comparing those, you would assume that since 21K has like a lot more variations and it's like a lot more, such a large data set, um, it should lead to a higher score, the but there is actually no significant increase between 1K and 21K. So that's just and obviously so they've also compared
I think they
s-
also say
when
that the ImageNet 21K isn't actually that much more diverse than ImageNet 1K, right?
yeah, it's just larger, it's not diverse, yeah.
Yeah.
So it does not actually so the quantity actually is not reflecting off to the the increase in score that one might expect. Even in when they compare language alignment, which I'm going to talk about. So yeah, in comparing all the models with Meta AI, and they actually compared it with the OpenAI's Clip, the Clip performed the best, which obviously has the language alignment. But when compared to the language alignment of the the Clip model of Meta, which was released by Meta, it is not actually so one interesting observation over here is like if we actually see the Clip model of Meta, which has a language alignment, it has a slight negative correlation between the brain activity, just a very slight between the brain activity and uh, the language alignment. But OpenAI's Clip performs the best, and that's the author's claim that that's not because because the Clip is language aligned. It's because the Clip was trained on a data set which was not released to the public. Like it was first trained on like 400 million images, which this highly curated and proprietary data sets of 400 million image text pairs. So it's not actually because they're language aligned. It's because uh, they've trained in such a good data set. So it's so the data sets that diversity and actually matters a lot. And like in the conclusion, they actually say that there's actually no clear metrics to determine how do we have the best dense like the best diversity in a model. Obviously we talk about SSIM scores and everything, but that has not been implemented into the model, but since into the data sets. So seeing the data set being such a high indicator of how the brain predictivity can be can be determined. So that is something what these authors are suggesting people to work on, is to have more diverse data sets. So a data set is clearly the biggest uh, biggest factor in determining the predictivity. Yeah.
It makes me think that like maybe this is the way to quantify image diversity. How diverse was your input images for training your model? Let's compare it to the brain.
Yeah. Mm. Oh, yeah, we can actually, yeah. Mm. But then again, for that, we need a much diverse data set to actually train the model first. Because these all models are trained on ImageNet, and then they use the NSG data set to actually pass on the images and the voxels. So yeah, it's all about the data set, it seems. So they also
Wait,
use
so does that
yeah.
mean what were you saying there? Would that work or not, you think? Like the fact that it's NSD, yes, that means that we're using specific images, but these plots, like the models were not trained on COCO or NSD. So,
They weren't.
like, is it still a perfectly fine proxy for quantifying the diversity of the models in terms of the image diet?
I mean, it should be. The only reason, so they haven't trained. They're using NSD because we have image and fMRI pairs with NSD, but they're not essentially trained on. Wait, so does the ImageNet have the same COCO images? Because NSD just uses COCO images, right? They don't. Okay, so I mean, for inference. I think for inference, they are using the images which the models haven't seen, which means that using a different data set to test out whether the model has this image embeddings means that yeah, so it's a good indicator of how or if the image models are trying their best to, or if a model can actually understand those, or has the, can actually produce the image latents which actually relates to an image. Like these images which are being used to calculate the Pearson score, they're actually not part of their training data set. So I think, yeah, it should work if the model is working well, which the whole argument around this paper is that we have good functioning computer vision models. So yeah.
Yeah, I'm just kind of curious about that because it's like you wouldn't think in order to quantify how good the input image variation of all these different models is would be to basically take brain data from a separate natural scenes data set of COCO images, and then somehow that boils everything down to specifically the input image diet as being the prime factor of like what's causing the difference in Pearson scores.
Yeah. So, yeah, so essentially they just use
Maybe there's like a more straightforward way to measure image diversity, right? I imagine there would be, but if there isn't, then this would be a kind of wacky way to determine who has the best image variation across models.
uh
Yeah,
yeah,
I've never heard of a good way to measure today.
yeah.
I definitely heard people talk about it before. But
This paper mentions that there is actually not a good way of like not yet. There is not a lot of people who are actually talking about diversity amongst the data set, and there's actually not a way to actually calculate it. So I'm not actually sure. This is the first time I'm actually hearing about diversity within the data set.
Yeah. So it's
So
like, yeah, one data set might be bigger, but maybe it's not better. But also, a lot of these companies do not open source their models. So, like, you have OpenAI's models, you have Anthropic model, I don't know, any sort of closed model that you want to evaluate who has actually the best data for training. Like, I guess this would be one way to do that without having access to the actual training images.
and maybe that's why OpenAI hasn't released the data set on which they trained Clip because it's just so good. Like it just because of their training on that data set, it's like it's better than all the models that were just trained. All the meta models that were just trained on these other data sets. So yeah. So like in language alignment, it basically doesn't matter if the images are aligned with their Kobo captions or just their captions. So, but before that, let me just get into the self-supervised algorithms, which I kind of think is interesting. So they did test out with some self-supervised algorithms, which so it's like simpler and Barlow twins. Uh, to see how they compare with each other. Um, so simpler was like pure self-supervision, which and clip was like pure language alignment. And then there's another model called SLIP, which is partly language alignment and partly self-supervision. So, across all three, there were no substantial differences between the Pearson scores of all three models, although there was a slight decrease in the pure language trained, the clip. So there was just a slight decrease in here. Not sure if that's significant. I don't think. So you can see there is like a slight decline over here. But all in all, these self-supervised models, they achieve the same Pearson scores for brain predictivity. And so because of that, the authors, came up with the conclusion that the superior performance of OpenAI's Clip is actually not because of the language alignment, and it is mostly because of the private data set that they were trained on. So another yet again, indicator that the data set actually plays a major role uh, in getting this brain predictivity to work. Yeah.
I think that
Yeah.
result is super interesting and also kind of challenging for the previous talk we heard. Aria Wang, right?
Yeah, they
She
call
did that.
her
Yeah,
work
yeah.
out in the paper.
Yeah, that was pretty cruel. Didn't like that. But I think there's another possible explanation here, which is
They
the
did kind of have to
YFCC.
call it out though, because it
They did have
conflicts
to,
with it,
I
right?
guess,
Like,
but also the YFCC dataset might have bad captions. Like, are their captions
Could be.
good? Is it a fair comparison? If you start with a data set, yeah, sure, it's a data set where all three models have been trained. But if the captions are not sufficient to train a good clip model, then it's not really fair. Honestly, I think if you want to do, this is part of a larger point, but I think this paper and also Aria's paper and lots of these papers have a challenge to deal with the fact that they're all taking models off the internet and not training their own models. And so they're all forced to do kind of difficult, confounded comparisons that are not very clean. Like ideally, you would train every single model on line 2B or something like that, some recent data set, and then and train them all with exactly the same compute budget, exactly the same team, training them all, and do a really fair comparison. But that would cost $1 billion.
Yeah, they used around like 166 I mean, actually they used 224, but out of them, 60 were untrained. So they used around 160 models in the PyTorch imaging library to actually get these results. So in just getting these results, it was around 1.8 billion regressions. Just imagine how much if they actually had to train each and every one of them. Like even in the footnotes they mentioned to replicate all of the results that we have just mentioned, it'll take like weeks. It'll take weeks of training time on like 8 RX 3090. I'm like, I can't even get my hands on one. They need 8, and then they're running it for weeks. And this is just to get these results, not to account for training, which for some of the models take days. So I don't think that was possible.
Yeah, totally. So I just think confounds are
Uh,
part of the
mm,
game here, and no one is uh, insulated against confounds when they're using these off-the-shelf models.
yeah.
what were you saying though
Uh,
about the because the reason why they talk about the Aria's paper, specifically calling it out, is because I think in Aria's paper, right, they talk about how, like, the ResNet 50 was, or AlexNet, whatever model that was like better at early visual areas, and then Clip was way better at the higher level visual areas. And like, so like But what was it exactly that they call out for that paper?
Yeah, so the issue as I understood it is that when doing comparisons with OpenAI Clip, there's two possible explanations. One is that Clip, the model framework, is better, or two, the Clip dataset is better. You don't know which it is since we cannot access the Clip dataset.
I see. So basically, Arias was talking about like using Clip with language image. It can be a better model, but maybe it's because of the image data set, and that's the
Yeah,
difference
the
in
images are
interpretation.
richer. Yeah.
Yeah, okay.
But in this case, you have YFCC. Honestly, don't know if their captions are good enough. And if you have good captions, which I'm sure OpenAI collected good captions, and probably Lion2B has good captions, or whichever the state of the art open clip model dataset trained on that, you would ideally take a dataset that's good for clip and then train a vision only model on that dataset and see what happens.
Mm-hmm.
Yeah. Yeah, so basically it's like we don't really know if these models have a good alignment between image and the text, right? Okay. Yeah. Yeah, that's a fair thing. But yeah, so all of this, just points. So next they tested out uh, how does the input diet or the data sets differ with the brain predictivity, and this is where most of their conclusions come from. It's like, so they tested out ImageNet, uh 1K versus 21K, and well, they observed no, as I mentioned, they observed no real effect on both CRSA and VERSA for when comparing these two data sets, even though 21K has like a lot more images, but it's not as diverse as 1K, or it's not more diverse than 1K. So they have very similar scores. So even if they have like more classes and more images, it is not reflecting off to a better increase, better increase in the scores. So yeah, so it really just means that the raw quantity of training data does not necessarily lead to an increase in predictivity. Um, and I mean, yeah, but even the 21K data set is not as diverse as 1K. So that means that that probably explains why there was not an increase in the scope. And apart from that, they actually also use the data sets which were focused on object detection. Um, so open images data set, or the data sets which are focused on scene. So they use Play 365 for that, and data sets which were all based on the face. Um, so there's VGG phase 2. And well, the results were pretty much as you would expect. There was a decrease in the scores of in brain predictivity when we are using data sets which are specialized. And for VGD phase 2, it was even worse. So at least for this architecture, which was just a ResNet 50 and these objectives, the visual diet is a substantial indicator, indicator and a substantial variator in for brain predictivity. And the diversity is one of the most important thing in it. So latent diversity in a data set obviously proves that it is one of the most important factor in determining the brain predictivity, as confirmed because they use these data sets and the results were even worse. And also a thing to mention that these data sets, so like these open images and place 365, they are much larger data sets than ImageNet. So this again, really proves that the quantity of the images does not really matter if the images are not diverse, like the data set is not diverse. So as you can see, it is like 2.75 times, 1.5 times the ImageNet, but it is still has a lower score than ImageNet.
Yeah, importantly
So
though, this is all on occipitotemporal cortex, which is like a big swath of the brain. And I
yeah.
know that that includes regions of the brain that are specific to objects, places, faces, but it's not like they specifically looked at ROIs of like specific brain regions like fusiform face area, parahippocampal place area, modular kind of areas of the brain that are known to specialize in a specific kind of image processing. I wonder if that would change things.
Okay, so these V1, V2, V3, V4, which are the visual, so okay, so they lie inside this occipitotemporal cortex, right? OTC.
Yeah, it's all, I think OTC is what it's like in the figure you can see it's basically visual cortex and yeah, ventral,
Oh,
temporal. So like the very back of the brain is going to be the early visual cortex stuff, but there's modular high level regions of the brain like fusiform face area that are more, you know, lateral underneath the brain, farther away from early visual cortex that are very specific for processing faces in that case. So if you isolated just
uh,
that brain region,
yeah.
then maybe having a model that is specific to faces would actually be more helpful.
Yeah, it'll be interesting to see how activations in each of the visual, V1, V3, V4, vary across different factors. Right now, I think they're just averaging out, just mentioning OTC. They're averaging out
Yeah,
across
and
all
they're doing
the
this kind of
subsegments.
like weird random projection thing, which I don't know if that's gonna kind of preserve these modular representational things that are known to be the case in the brain.
Yeah. Yeah, we don't actually know which parts of the OTC are actually being activated. It's just averaging it out. Well, yeah, it's just averaging it out. So yeah, it'll be interesting to see how this varies across different ROIs. Uh, yeah,
Like imagine if it
but I
didn't. That would be pretty incredible to see like, okay, this specific region of the brain known to only process faces. If you use an image diet that it doesn't really have that many faces in it, but it's very diverse, what if that actually has the better Pearson scores than the,
yeah, exactly. Yeah.
yeah, right? Like that would be kind of
Maybe
crazy.
if we just, yeah, maybe if we just use this place 365 data set, maybe just activate some different parts of, different ROI, which is not, which, differs from, let's say, face. And so yeah, it can help us map out these different ROIs, which I think they're already mapped out. We actually know different parts of the brain activate for different phases, but this is like we can track changes over time in terms of data sets and uh, different factors. So yeah, that is one of the things we could actually look at. I I'm not sure why they've just used the whole OTC. Hmm,
Well, they're doing 1.8
Maybe,
billion regressions. Maybe it's
yeah,
enough to
maybe.
pick one swath of the brain.
Yeah, I mean, everything
So
just
there's
comes
got to
down to
be a
120.
paper. There's got to have been a paper or like at least a poster that compared models trained on face-only data sets versus general data sets in terms of brain prediction performance in FFA. They must have done that. I'm sure they did that.
You think so? Like, I don't know if other papers have been this scientific in restraining those models that they're using in terms of like all these parameters that they do a great job in this paper of isolating, like image diet versus task versus, you know, architecture.
Yeah, I think It is conspicuously missing, I think. Maybe they're like holding it out for a separate paper or something to do
It'd be
like
an
a more
easy enough
fine-grained.
second paper, I suppose.
Sorry, what?
It would be a simple enough second paper for them to do. They've already got all the code in place to do this on OTC, right?
Yeah, just kind of split it out by ROI. Yeah, I'll look around, see if folks have done that. I would expect somebody in the Nancy Kamish orbit to have done that.
It would make sense. Yeah.
Right, so in the NSG data sets, I know we have these voxels available. So can we make out which part relates to which ROIs? Like right now when I was like looking for algorithms, so we have like 3 by 39K size of boxes. So are they actually flat? Like, are they actually flattened, or this is how they are? They have to be flattened, right?
For the NSD data set, are the voxels flattened? Is that what you're asking?
Yeah.
Not initially, no. We have the full 3D.
Okay, so after flattening, it was like 3 by 39K, dimensions of matrix. Okay, so when we have that 3D thing, when we have those in 3D, we can actually map out which part of the boxes out of which ROIs, right?
Yeah, you can do it either way. Like they give you for the natural scenes data set, they give you the ROIs. So you can flatten the ROIs the same way that you flatten the
Oh,
actual
okay.
brain, and then just like do the indices comparison to see which vertex or which voxel corresponds to each. And also in the algonauts themselves, they give you files, I think, in the challenge space where you're able to match the ROIs accordingly.
Oh yeah, I did see that, yeah. I mean, yeah, so if they're already doing this for OTC, I think they can get the similar results for each ROI. If assuming that we have the data which correlates to each ROI, so I guess we have that. So
But it's like
yeah.
the sort of big picture point here is that they're sort of saying that these models are not really that important. Like all the differences between these models, so architecture, CNN versus transformer, the specifics of the task, these don't really matter as much when it comes to understanding brain, like in terms of being able to better predict with an architecture that seems to fit better with how the brain actually works. Like a priori, you might think CNNs would do better because that's more similar to how brain hierarchical, like how the actual brain works, but that's not the case. So it's sort of like, okay, is there anything usable with all of these models for better understanding how the brain works? They find that the major thing is just the image diet can delineate which of the models is going to predict better, but that's not really theoretically exciting, I suppose, for us to better understand the brain. You know what I
Yeah,
mean?
but they came at that conclusion that, it's only the data set that matters, because they take the whole of this ODC and uh, they get its high representation latents, which averages out uh, the differences between each of the ROIs. So just because just because using a VGG phase data set means the correlation score actually decreases, doesn't actually mean that doesn't tell us that if that doesn't actually tell us that the activations in the regions of interest, which have been known to correlate when humans see the face, are actually being correlated, are actually being activated. So they're just averaging out to get and generating these latents.
They're
So
not
we don't actually.
averaging, are they? They're doing this random projection thing, so it's not exactly averaging,
It's not
right?
exactly averaging, but how do we know the variations within the OTC when we have for
Right.
getting
But
input variations.
like the initial take from this paper is sort of a pessimistic, we're not really learning that much about the brain from
Oh yeah, it's a
comparing
pessimistic
the different
paper.
architectures of models. But maybe the reason for that is because of what you're saying, of like, this is a very broad analysis. They haven't tried looking at hierarchically, like
Oh, okay.
different brain regions. Maybe
Yeah.
you're this random projection thing, or the fact that you're doing it across a single brain region is maybe muddling the results to give you that cynical kind of take. But if
Oh
you
yeah, that might be.
maybe did more subtle kinds of probing of specifics across the hierarchy of the brain, maybe then it turns out you get a different result.
Yeah, 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 that's a good point. It's maybe because we're looking at the whole ODC. Yeah, because it's a very pessimistic paper. It's just uh I like there's no relation between CNNs and transformers, uh just a data set. And yeah, maybe it's because it's just such a generalized study and not on the basis of actual ROIs, which I'm really interested to see if there are actually papers which describe how brain predictivity and certain ROIs change in respect to uh, different data sets or different images. Uh, yeah, I guess that's one of the main problems in neuroscience, to understand which part of the brain gets activated in response to which images. Although I have read about some ROIs which get activated when there is a image, and there's a different ROI when there is a face in front of us. Uh, but we don't actually really know which part of the brains get activated. So uh, yeah, I'm really interested to see if there are other papers for delving deep into this. Um, yeah. So next up, they actually tried out if training actually leads to a higher Pearson score, and I mean, obviously it does. So out of like four models they tested, they also tested out a model which is not being trained and just randomly initialized. And obviously, it has the one which was not trained had a very low score. There's a graph. Okay, so it's actually this is one of the graphs I wanted to focus on. It's like all the 126 models that were just tested, they had, this is what I mentioned earlier, they had a delta of Pearson of around 0.1. This drop that you mentioned is mostly because of the data set, and it drops down to an area where the models were untrained. So at most, it just seems to me it's like most of the time it's the data set that's the significant, you know, character in determining the brain predictivity.
Can I
So
challenge that real quick? I
yeah.
want to kind of challenge this. Looking at this figure, I get that their message is that the data set is the main factor, but this is not obvious from the figure. I think like all these black markers are from the ImageNet, right?
Mm, yeah.
And then you got like two markers from places and bases, and then you got a bunch of like these whatever tan markers from taxonomy. Um, and so the claim comes down to the steep drop that we see around the taxonomy models is supporting the data set is important claim. These taxonomy models, they're just not very well trained, and the task is not very good.
Or or it actually, correlates that the task actually does matter when determining brain predictivity. So if there is a semantic segmentation, that if a model has been trained on semantic segmentation, those learnings does not transfer very well into predicting the brain predictivity. So although that's also a factor that the tasks of these models actually does matter, It's also the diet. So yeah, you cannot arbitrarily say from this graph that it's just the model. It's because there are different models as well. Um,
Yeah. There's
Especially
only
in
4 data
taxonomy. Yeah.
sets used. There's like
Mm.
countless models and architectures and tasks and only 4 data sets. I would like to see one model trained on different fractions of ImageNet.
Although their argument for only using ImageNet to compare all of this is just like they wanted to keep everything same and just have one thing different, as an inductive bias. So at least, so since they're comparing all of these only on ImageNet dataset, they're hoping that whatever the reason and changes in the Pearson score is attributed to the types of models and their diet and the types of their tasks and not actually the data set. But although we've seen in the other graph, it means that the data set actually also matters. So yeah,
I just think
and
it's hard
obviously, yeah,
to conclude the data set point when there's only 4 or
and there
5
is only 4 data.
data sets. 5
Well,
data
to be
sets.
fair, these data sets they're not very diverse. So you can't even compare these data sets to ImageNet, which has like a lot of images. They're like very focused data sets focusing on scenes or faces. So
What about open
yeah, you can't
images? Thought that was like
open
an
images.
ImageNet replacement.
No, it's just based focused on the objects. So it's based focused on object. It's not as diverse as ImageNet, although it is much larger, but not as diverse. So you can't really even compare with ImageNet.
I don't know. I think open images was supposed to be a good data set from Google with like a lot of
Oh.
good stuff about it.
Is it as diverse as ImageNet? I'm no
What do
clue
they say?
because this paper mentions that it's an object-focused data set and
Yeah,
not like a
it is
ImageNet is
kind of like
also
a
like
Coco replacement, but yeah, go ahead.
ImageNet is not like by itself like the golden diverse image set. Like
yeah.
there's plenty of problems with ImageNet too, and also they do have a focus, I think, on objects in ImageNet. Like maybe not to the same degree, but usually there's a focal object in images in ImageNet, right? It's not usually a cluttered scene of several different objects.
Yeah, very true.
Yeah.
Like plot the heat map of the bounding boxes. It's like right in the middle.
Yeah.
So is
Yeah.
there a data set which is like actually balanced with everything? And
There's
that's what
definitely
I
better
mean.
data sets than ImageNet.
Oh,
I mean, if you want real like diversity, it kind of like depends. Like, I don't know, is Lion 2B, is that diverse? Because they're basically just scraping everything, right?
Yeah, I
it's,
think that one's good. I think
is Lion to be just is yeah. I guess the one of the things about Lion to be is just because it's like is the sheer size of it. I don't know
They're
if it's
400
as
million.
diverse. Yeah, it's like they have like 2 billion images, but are they diverse enough? Again, this paper actually says there is actually no way of calculating how diverse a data set is. That is something that people need to work on.
yeah. I
And
think the
here we are discussing the same thing.
Dino V2 paper does a good job like trying to address this issue. They construct a new data set. They take care to try to make it like quote diverse in some way. Um, they come out with a data set with like 140 million images.
Mm.
So not the biggest data set, but well curated, and they're aiming for diversity.
And did they use Dino in this paper?
No, it's not in this
No,
paper.
But it is in the deep dive GitHub, which the author made. So
I
Is it?
have I have not read a single instance of Dino, not gonna lie.
why didn't they report Dino if it's in the GitHub for the, they have their own deep dive GitHub that automates using all these models. And I looked and Dino was in it, as well as a few other models that I think are not in the paper.
It could be a difference of the Dino V1 versus V2. V2 is pretty recent and pretty different.
Mm.
Yeah. Yeah. They also tested out if the representations, so like if a model, so they also tested out if the affected dimensionality plays a part in getting the brain predictivity, getting a higher Pearson score on brain predictivity. Basically meaning if these model representations, if they have a higher, if if these so okay, so the model's latents, does the complexity of a model have to do with how accurately it predicts the brain predictivity? So they did test out uh, the to test out this relationship between ED and brain predictivity. Although yeah, so there was no among the trained models, which were already trained, there was no real correlation, and untrained models, which they don't have higher scores anyway, there was actually a slight negative correlation, but it's not statistically significant. So although it does mean that having a more complex embeddings lead to a higher CRSC and VERSS score, as mentioned in these graphs, but it's mostly because of it's not because they're more complex, it's because the models that are being used to compare, they're trained they're either trained or untrained. So if there are trained models, they have a higher RSS score than the models which are untrained. So it's actually not related to having a more complex or a higher latent space. So so there is no actually real correlation on effective dimensionality as well. So I mean, as you just go down, there is no correlation in most of the things. So yeah, it's right here in the graph. So, I mean, moving on next, they also tested out classification accuracy, and this is also something I mentioned before. Um, so this time they tried with the models which have a higher accuracy score. Like the previous work suggested that there will be a higher correlation if these models have a higher accuracy scores, but the newest study said that there is actually no correlation. And even with this, even when these authors tested it out, comparing the models which have scored like in the top 1% of ImageNet 1K, uh, had little to no correlation between the classification accuracy versus the brain predictivity. Uh, so yeah, even with testing out with the models which had a wide range of accuracies, there was a limited range of brain predictivity. So even though some of the models might have from let's say 70 to 80% accuracy, even if the range of accuracies have a broad range, uh, the the brain predictivity scores were not differing that much. So even the classification accuracy at some point is not a very good indicator of predicting, the brain predictivity scores. They also tested out the number of images, the number of trainable parameters. So there are if there's a regular state of increase in the parameters, if that's going to be a factor for brain predictivity, but they they got various amounts of irregular set of patterns. So if there was this increase in trainable parameters, there was a decrease in CRSA score. but a non-significant increase in VERSS score. So there's not a consistency in the number of trainable parameters. So it was like, I, the number of trainable parameters also does not really matter in terms of getting the brain predictivity scores. So yeah. Um, then they, after figuring it out, like after getting all of this, wait, let me see. Yeah. So they also did model-to-model comparisons, which was basically a study of comparing different models to see if they can actually identify, give me a sec. Um, wait, where was that? Uh, yeah. So comparing model-to-model comparison was mostly about comparing if a particular model, if like the two particular models have the same understanding or a similar understanding of the images. Basically, when they compared, the most brain-aligned layers of the top 124 brain predictive models, there was a vast variety of similarity between these models. Even though these models were like, let's say, from CNNs to um transformers, they were getting at the same representation space, even though they had a very different architecture. Um, and yeah, and these authors also mentioned here that although these, what we've talked about, number of trainable parameters, the types of models also matter, what also matters is, you know, the metrics that we are using. So CRSA versus voxel encoding RSA. Because as I mentioned before, it's like 31% of the variation across the voxels in the NSG dataset is being explained by CRSA, but over 79% is being explained by the ERSA. So it's definitely the reweighting of I need to get more deeper into like what reweighting actually works and how it actually works. But this is definitely, playing a major part in explaining the variance across in this NSG data set. And yeah, that's what the whole paper is all about. In the gist is like uh, there are parameters which we use to improve the accuracy of a deep learning model, and we would think that these parameters would also improve the brain predictivity scores, but most of it actually doesn't. It's mostly about the data set in this case. So yeah, that was the whole paper.
Yeah, thank you so much for walking us through the paper, Mihir. Great overview of everything.
Yeah. I mean, yeah, even I wanted to deep dive into this paper anyway, so I was like, I'll do it and still have to, learn more about how they reweight those. So yeah, there's that.
Yeah, and I think there are definitely some open questions here where I don't think we should be totally pessimistic about the possibilities of, there being actually interesting connections between different kinds of models and mapping them to the brain.
Oh yeah, definitely. We should actually explore more how it varies across regions of interest, if anything.
Yeah.
Yeah. It's a really, really interesting paper. Wow.
Yeah, I agree. This was a really high quality paper. I'm glad that they were able to tackle this, and it's not an easy effort to get all of these
Oh
models
yeah.
working. It's pretty crazy, actually, that they got this to work.
Yeah. It just to replicate, it will take like weeks to, just get it done. So yeah.
Oh yeah, totally.
Mm.
All right. Any last thoughts from you or Connor? All
I
right.
think I'm
Well,
good. And thank you so much for walking us through the paper. It's really fun to go through it.
Yeah,
yeah.
no worries. It was mostly for I wanted to understand this paper, so might as well. So that's all.
All right. Yeah. Thanks so much. See you guys around.
Yeah. Yeah. See ya on Monday.